Okay, hi everyone. It's week 12. Today we'll be talking about NP-Completeness. So this is meant as like my recording to make up for, because today is actually a public holiday, but there are some of you here. So thanks a lot for coming, although it's a public holiday. Yeah, so I'll just begin with NP-Completeness. I think it's a continuation of last week's week 11 on reductions. So quite a number of ground to cover as well. Okay, so these are the things that I'll cover today. We'll start off with the complexity classes. What's P, what's NP, what's NP high, NP complete, and so on. And then some questions related, which might help you for the upcoming assignments. Okay, again, announcement, assignment 3 is out, which is due next week, Wednesday, 2359. And they're about reductions and NP completeness. And in fact, today's class, I think, should be pretty useful in understanding how understanding question or how you might progress. And of course, please try to start early. Reductions can take up a while to come up with and for you to prove. Okay, maybe even if you did early and you realize, okay, I have a solution, eventually you might, hopefully not, but sometimes you might realize, oh no, my reduction was wrong. Like you proved it wrongly, you know? So these kind of things can happen. A small tip, I guess, is when you're doing reduction questions, because the problems are typically new, like in assignment, there's this thing called the dominating set. And maybe you want to draw some small examples, small graph examples that you can use to understand what is exactly a dominating set. Okay, so all right, let's begin with complexity classes. What is it about? So last week we talked about reductions. We say that A is polytime reducible to B, or this is a polynomial time reduction if it transforms input A to input B, such that input A is a yes instance, then it implies input B is also yes instance. Then we also prove the vice versa. So it's an if and only if input A is a yes instance, if and only if input B is a yes instance. So you need to prove this property, especially important when you're proving your reduction. Okay, so transformation takes polynomial time in the size of input A. Sure. This is what it means for the reduction to be polynomial time. Okay, then again, I keep reminding you, it's important that you get the direction right. This is especially important for this topic because you'll be showing whether the problem is NP complete. You'll be showing whether a problem is NP hard. You need to start from a hard problem. Okay, so you start from a problem known to be hard, and now you know better. You start from a problem known to be NP complete. Okay, we'll talk about that in a bit. So again, a note on the polynomial time is that we usually discuss it with respect to the encoding of the input. So just keep this at the back of your heads. Okay. Then, all right. This was last week's stuff. Any quick questions maybe? Okay. So, okay. Then I'll talk about complexity classes now. What is it about? So I'm not too sure how in-depth it was discussed in lecture. But okay, so we will learn about complexity classes, P, NP, NP hard, NP complete. And to build up intuition, I will use this kind of like number line, number line, but it's more like hardness line. So going from left to right is getting increasingly harder. Okay, so okay, P is a set of decision problems, right, that can be solved in polynomial time. So it's in the leftmost side of the difficulty line, the hardness line. Okay, so it's over here. Then, for example, problems that you have done so far, most of them are in P. Okay, so it's either shortest path, minimum spanning tree, things like that run in polynomial time. Okay, so NP, right, is a set of decision problems whose yes instance can be verified in polynomial time. So what does that mean exactly? Let me talk about that. But in terms of the difficulty, the hardness, it kind of covers both P, but it goes, okay, it is unknown whether it goes slightly beyond or not. But for pictorial purposes, let's do it like this. Okay, so it's somewhat extends, somewhat harder as well. Okay, so NP stands for non-deterministic polynomial. It's not non-polynomial. Okay, so why is it called non-deterministic polynomial? That's because there's an alternative definition to NP. Let's not talk about that. That's not the focus of the tutorial. But what does it mean that the yes instance can be verified in polynomial time? Okay, in the lecture, you'll hear the term certificate. Certificate is just this other term just to mean a proposed solution. And verify in polynomial time means that your algorithm can efficiently check that the proposed solution is correct. Okay, so the intuition is that, you know, it's easier for you to check an answer key and thinking that the answer is correct rather than coming up with the correct answer yourself. Like for example, like even in tutorial, right? If I go through the question, it's easier for you to verify whatever I'm saying is correct rather than coming up with the answer yourself. Okay. So for examples, all problem in P is also in NP. I'll explain that soon. Then problems like tree set, vertex cover, independent set, these problems are also in NP. Okay. So what does it mean, right? Like let's go through an example. Like how will we confirm whether something's in NP or not? Last week we talked about this problem. Given a set of positive integers S, can it be partitioned such that the two sets have equal total sum? Okay. So a certificate is a proposed solution. So you have to give a format. Okay. How will you try to verify whether someone is giving you an answer or not? Okay. So the certificate here is the two partitions, right? The two partitions, the left partition and the right partition. Okay. So someone comes along and tells you, hey, let me propose to you that this is the solution to this problem. Then you, as the verifier algorithm to verify that it's in NP, run some check to see that, hey, is this guy really making sense? Is this guy really like trying to convince me that this input is a yes instance? So the verifier algorithm, it does sanity checks on the proposed solutions. Okay, so an idea for this particular partition problem is that it sums up both partitions and check that they're equal. That's the criteria of the equal total sum, right? The partition into two equal total sum. Okay, so but is this all that you need? Okay, think about it for a bit. First, understand this slide what it's trying to say first. Then, do you think like this is all that you might need? Okay. Okay, if I'm asking clearly, there's a bit more. So something that I think a lot of people would miss out is checking that the elements in the proposed solution also matches the input. And why is this like a step that I think is important for you to remember is because, well, somebody can come along and tell me, hey, the answer is like 1, 3, and 4, right? Someone tells me that, hey, the answer is 1, 3, and 4. This is the solution to this yes instance. Well, if you only have step 1, then it'll pass. The verifier algorithm will say, okay, I'm convinced both partitions sum up to equal, right? Sum up equal total sum. But however, as you can see, the partition is in nothing in the input says that it has 1, 3, and 4. So that's why you need also to check that they also match the input. Okay. All right. So let's go on. All right. So just to summarize, what you need to show that a problem is an NP is that to first come up with a certificate format. You need to show how does your proposed solution look like. In this case, my certificate format is that the proposed solution looks like two sets of numbers. Okay. Then design a polytime algorithm to verify to see that in this format, what do I do with this format so that we can verify that it is indeed a solution. This is like AI when the criteria is odd and you get weird outputs. AI is weird. Yeah. So anyway, yeah. So this is how to show whether something is in NP. Okay, so any questions about that? Because I think in lecture, it might not have been explained explicitly. I see questions in the forum. I see some people PMing last week. Okay, if not, then I will go on. So now let's discuss a little bit about the class, right? P is a subset of NP. Okay, so if a problem is in P and you are given a proposed solution, let's convince ourselves that every problem in P is also in NP. And you are given a proposed solution to a problem in P. Let's say a shortest path problem. Somebody tells you, hey, this is the shortest path. It gives you a series of edges, and this is the shortest path for this problem. How do I check? Okay, how do I check? How do I verify in polynomial time? Okay, so, well, the idea is just run the polynomial time solution to the problem and cross-check with the answer, right? So you know that there's a polynomial time solution for the problem. So what you can do is that you can just use the solution, the polynomial time solution, solve the problem at hand because it's in P, right? You have a polynomial time solution, and then cross-check with the proposed solution. Hey, does it match or not? Okay, so therefore, every problem in P is also in NP. This is what it's about. Okay, this is just argument why P is in NP. What about NP hard problems? Okay, so NP and NP hard, both of them contain the name NP, but they are different things. Okay, they are very different things. So NP hard is a set of decisions that are at least as hard as the hardest problem in NP. So hardest problem in NP, in case it is a number line, this is like a vertical line here, right? So at least as hard as all problems in NP means that it's here onwards. Okay, so this is NP hard. And how to know if a problem X is NP hard? Well, stay tuned. I'm going to talk about it in a bit. And so just know that NP hard just means at least as hard as the hardest problem in NP. Okay? Okay, so NP complete. NP complete is this set of decision problems that are NP hard and in NP. So it sits just nice at the intersection between NP and NP hard. Okay, so it's both in NP. So first of all, it's in NP somewhere here, but it's also NP hard. So it sits just nice at this intersection over here. That's what this means. Okay, that's NP complete problem. An alternative definition is that if a problem X is in NP, it is NP complete if for all problem in NP, we have a polytime reduction from A to X. This means this part is saying NP hard, which is saying hard, at least as hard as hardest in NP, as hardest problem in NP. Okay, so this is the alternative formulation. But I prefer like thinking about it in this way. This will make it easier because you'll be proving problems in the tutorial to show whether something is NP complete. Okay, so the intuition, they are the hardest problem in NP. And hey, hardest problem in NP. Didn't we hear that before? Okay, so the hardest problem in NP, then this is directly linking with how you might show a problem is NP hard. Okay, so how do we do it? Is that how to know if a problem X is NP hard? Is first you take any problem A that is known to be NP complete. For example, tree set, which we might have seen in lecture, then show that we have a polytime reduction from A to X. Okay, we have a polytime reduction from A to X. So again, remember, get the direction right. You start off from an NP complete problem. Start off from an NP complete problem. Start from NP complete problem, reduce to the problem that you want to show is hard. This is especially important for this week's assignment, okay? So if you want to show some problems in NP complete in the assignment, there are two of such questions. Get the direction right. Start from an NP complete problem, start from an input to an NP complete problem, and then transform it to the problem that you want to show that it's NP hard. Okay, so now that's step one. No, this is to show that it's NP hard, so this is fine. Later on, I'll talk about how to show it's NP complete, but really it's a simple extension. Okay, so any questions about this slide, this whatever we have so far? 916. Okay, if not, then I'll go on. So the biggest unanswered question in computer science, and really this is like my virtual background, P equals NP, is whether P is equals to NP. No one knows, right? So something like this. You see there's this gap over here that I deliberately left out, but people don't actually know. Is there something that is not in P? but it is actually in NP, something in this gap over here. Do we know if anything like such thing exists? Okay, we don't know. No computer scientists know. But many scientists believe that P is actually not equals to NP, right? And this long quote by Scott Aronson says that if P equals NP, then the world will be profoundly a different place, right? So remember, P is about like getting solutions in polynomial time, and NP is about verifying solutions in polynomial time. Okay, so the essence of this quote is saying that if P goes to NP, then it's that you coming up with a solution is not as impressive as like you being able to verify the solution, right? So if you can understand proofs in 3230, then you are as good as being able to come up with all of these fancy things in tutorial, okay? The essence of the quote is something like that, right? So you say everyone who could appreciate a symphony will be Mozart, right? Because maybe like you being able to appreciate music is as good as you being able to come up with it. Okay, so this is the essence of like what this quote is saying if P equals to NP. Okay, and there are many problems known to be NP-complete. Like I gave a screenshot over here from Wikipedia, but if you open the Wikipedia page, there's a lot more, so much. But the magic is that if we know one polynomial solution to just one of them, we'll get efficient solution for all of them. Okay, the magic you just find for one, then you get for all. But the main reason is because they are reducible to each other. Okay, so NP-complete problems, you can reduce, they are all the hardest problems in NP, and they can kind of like reduce to each other. So right now, we don't have any efficient solution. Many people have tried. So regardless like which problem they try, they cannot find an efficient polynomial time solution for them. Okay, so but maybe why should you care, right? So I was actually like throughout the years, I'm talking to a lot of people, and I realized that even in the industry, right, not just if you're a theoretical computer scientist, you might want to care a little bit about NP-complete, because even here, right, my senior on the left, he worked on the Ninja Van internship. Then he actually worked on problem related to traveling salesman problem, a generalization of traveling salesman problem. So it's known to be NP hard. And my friend over here on the right worked on something related to, I think, schedulers, and scheduling under certain condition is an NP-complete stuff. So this is in Shopee Tech Ops. In fact, right, like I think in one of my interviews for Shopee, I was given an NP hard problem for the coding test for like coding live coding stuff. Okay, so well, I don't know how you feel about it. I thought like, okay, I know this problem is NP hard. That means I've just brute force. So I don't need to think too much about coming up with efficient solution, just brute force. Okay, it sounds scary that you are asked an NP hard problem in an interview, but thinking about it, because no one knows an efficient solution, just brute force. That's probably the best you can do. Okay, and again, like why maybe you should care, maybe at work you are given an NP hard task, right? Something that it's unreasonable. Then you can just say that, hey, this is actually NP hard. No one knows efficient solution. What do you want me to do about it? Okay, so that's maybe like why you might want to care even if you're not going down the research path. Okay, so okay, great. So we covered what the complexity classes are about. Now let's talk about when is it that P equals to NP, because it's quite, maybe we cannot tackle it directly, but let's say we have other statements, right? So in tutorial, there's these things. There are statements that, hey, if I can show, maybe can I show one of these things, or is it not more of these things? By showing something, you might be able to imply that P equals to NP indirectly rather than showing a direct proof. Okay, so let's go 2 to 3 minutes to archipelago, and yeah. Let me know if you have any questions about the complexity classes. Okay, let's resume at 9:23. Okay, so the good thing about like less people in the class is you can easily keep track of whether like enough people have answered. So let's see. Okay, so right, so I see everyone has answered. This is and everyone got it correct. Okay, so I think this diagram really makes it clear of what it means when is it P is equals to NP. And the problem, if and all of you are right, option one is true. There's a problem in P, there's also NP complete. It implies that P equals to NP. Okay, why? Because intuitively, if there's a problem in P, there's NP complete, then this set is reaching NP complete, right? Like you can see it covers the entire set now, and P is therefore equals to NP in this case. Okay, so this is intuition, but if you want to be formal about it, let's use reductions, like use the concept of reductions and the definition of these classes. So if B has a polytime algorithm, then so does A. That's what it means for A has a polytime reduction to B. Okay, so formally, right, formally, NP-complete problems, well, there are also NP-hard problems. Okay, so really this should be like, there's an arrow over here. They are not, it's not all the NP-hard problems, but all NP-complete problems are NP-hard problems, and therefore they are solvable in polynomial time by, okay, wait, what did I say here? There is also NP-complete. So, okay, this is by following by the option here. It says that it is solvable in polynomial time because we now know problem P is NP-complete. So this is from over here. Okay, then all all problems in NP reduces to NP-hard problems, right? By definition. By definition, all the problem in NP reduces to NP-hard. Or NP-hard is at least as hard as the hardest problem in NP. Okay, then therefore, it means that NP-hard problems is solvable in polynomial time, implies that all NP problems solvable in polytime. Okay, so okay, this might be confusing, but I'm following from the fact that first of all, we have a polynomial time reduction, right? So this is the polynomial time reduction by definition of NP-hard. Okay, by definition of NP-hard, then because now we claim that NP-hard problems are solvable, we have an NP-hard problem solvable in polynomial time, right? There's a problem here that is solvable in polynomial time. That means we can invoke this property over here, where we say that if we have an NP-hard problem solvable in polynomial time, then so does A. So does A means so does this thing on the left-hand side. So does all NP problems solvable in polynomial time. And this also means that because all NP problems are solvable in polynomial time, then this is equals to the class P. This is like the more formal way to argue about it, but this is just me following definitions. So if you are lost, like maybe because the definitions are a bit everywhere, but again, just follow through the argument, look at the definitions, and realize that you'll also come to the same conclusion. Okay, any questions about this? Yeah, so I put it here. P equals NP by definition of P. Any questions about the option? Okay, if not, then let's go through the second option. So there's a problem in P that is also in NP. Well, this is false because we have earlier argued, like even the status right now is that we know that P is a subset of NP, right? Problem in P is also in NP, so there's nothing special about this. Doesn't say anything about P goes to NP. Then finally, there's a problem in NP that is also NP-hard. Well, we already argued that NP-complete problems are such problems we know to be NP-hard, right? NP-complete problems are in P and also NP-hard. So it doesn't say anything. This is the current status of the world right now. This is what we define NP-complete problems to be. Okay? So Okay, any questions about this tutorial, about this question, sorry? If not, then let's go on to the second question. The second question is about what if there's no polytime algorithm for problems in NP, right? So it says here, hey, I have an LNP problem. Then this dude managed to prove I cannot find a polynomial time for this problem over here. I have an NP problem, like somewhere in this range right here, but I cannot find a polynomial time for it. I proved that it's impossible to find it in polynomial time, right? So because of this, what is implied? Which one of these things is not known to be solvable in polynomial time? And factor is one of the options. So this is the definition of factor from the lecture. It's not a class of problem per se, it's a specific problem. So do we now know that it's not solvable in polynomial time? Okay, so again, let's go archipelago for 2 to 3 minutes. Let's say resume at 9:31 for now. Okay, cool. So right. So great. So we have everyone answering. So I guess we can just skip ahead and for the weight. And most of you got it right. It's 1 and 3. A couple of people thinking it's factor might be the answer. Let's talk about that in a bit. But intuitively, because NP is hard, right? NP complete and NP hard problems are harder. Like look at the number, the double quote number line, they are harder. So if NP is already hard, then everything else behind it is also hard. Okay, that's the intuition behind like the solution. Okay, so again, like as I said before, if A is hard and I have a polytime reduction to B, then B is also hard. Okay, so remember now L is hard. All NP, we show that all NP hard problems are hard. So L is now hard. Then L reduces to NP hard problems, right? That means NP hard problems are also hard. So this is intuitively what it means. Okay. Okay, cool. Then second problem, all NP problems. If we know all NP problems, sorry, if something NP cannot be solved in polytime, well, this is wrong. This is wrong because we know that P is a subset of NP. That means we know that P can be solved in polytime by definition. So this is wrong. Okay. The third option is really the same logic as I said from option 1. And intuitively, again, it's kind of like by the number line, it's harder, right? It's harder. So if we know NP is really hard, then everything else to the right is also hard. Okay, so this is intuitively what the answer is. The final option is somewhat like debatable. So the thing about factor, right? The thing about factor is that it's not known to be NP hard. We know from lecture, we know that factor is in NP, so it's in somewhere here. But we don't know where factor is. Like is it exactly over here, or is it here, or is it like where it is? We don't know. Okay, so kind of like, I guess, a trick question, because like no one really has an answer to it. This is like giving in tutorial is P equals to NP. We don't know. Okay, so just the thing is that we just don't know whether it's NP hard or not. Okay, and remember the implications is that only things to the right become like cannot be solved in poly time. Okay, any questions about this? If not, then we'll go to kind of like the main show of today. I'll wait for like maybe 20 seconds, if 10 seconds to 20 seconds, if anyone has questions before we go on. Let's see if I can do it in half an hour. Okay, I'm not too worried because I think like in the tutorial question, you all got it. Most of you got things right. So it's a pretty reassuring distribution. So let's go on to talk about showing the problem is NP-complete. And most of the time in excuse me, most of the time in questions related to this chapter, you'll be showing things are NP-complete. Okay, and even in assignment, maybe in exam, or maybe some variation that implies to show that you need to show it's NP-complete. Okay, so remember, you have a problem X and you want to know whether it's NP-complete or not. The steps are actually very routine. Okay, so you just have to mechanically follow this two-step. Okay, but the thing is, it's not easy to do. But again, you're doing the same thing. Recall NP-complete. It sits right in the middle here. It means both in NP and it's also NP hard. Okay, so it's NP hard and in NP. The first thing you need to do is to show that the problem X that you want to show is NP-complete. You show that it's an NP. So you show that it's an NP by giving a format. Remember, as I said before, you need to say, hey, what's the format of this solution? Format of a proposed solution, and then propose an algorithm to verify the certificate. As I said before, this is like the partition. The proposed certificate, the proposed solution is the two partitions, two answers to the partition, and then design an algorithm to verify that this is actually an answer to this input. Okay, so this is showing that X is in NP. Then the other thing you need to do, and no surprise here, is that show that X is NP hard, because that's the other criteria for X to be NP complete. Okay, so what I do is you take a problem A known to be NP complete and show that A has a polynomial time reduction to X. And recall, polynomial time reduction is you transforming the input of A. Again, I must emphasize the direction. You must start from a problem known to be NP complete. You must start from any input of 3 set. For example, 3 set is the NP complete problem. Start from any input of 3 set. Propose a way how you will transform this input to the problem that you think is NP complete. Okay. So again, as I said before, right, I really cannot emphasize this enough, especially I polled the class yesterday and I saw like 60-30. So I'm not sure if I should be happy or like said it's not even higher, but I think it's reassuring at least more than half the class thinks like knows the direction. So again, start for a problem you know is NP complete, which we'll show later on, and then transform the input into the problem you want to show is NP complete. Okay, so show a polynomial time reduction, and this is a summary of it. Okay, show that X is in NP, and then show X is NP hard. Simple two-step process. Okay, but the difficulty usually lies over here. Like this part over here is the painful part. Okay, usually showing something is in NP. Most problems is pretty simple. I think only like I've only heard one problem which might be difficult to verify NP, which is the primes problem. Prof might have talked about it briefly in lecture, but generally verifying things is in showing that it's verifiable in polynomial time is not as hard as NP hard problems. Okay, so let's now show 3 set to directed Hamiltonian cycle. So as you might have noticed, I omitted it from Archipelago. I think there's no point in asking this because it's quite a difficult reduction. So we'll show a reduction from 3 set to directed Hamiltonian cycle. So informally, what's 3 set? It's an N of 3 ORs, informally, right? So the formal term is that we have a literal. Literal is a single xi or a negation of xi. It's a Boolean variable or its negation. we have a disjunction of literals, right? A clause is a disjunction of literals, something or something or something, basically. A conjunctive normal form is the and of all these clauses. So take three things and take the other three things and, okay, this should be three, but sorry, this typo, this should be three. Okay, and something like that. And in general, given a CNF formula, does it have a satisfying truth assignment? So this just means that, okay, I have x1, x2, x3, and x4. Can I assign true or false value into these four things such that the entire thing returns true? This is the problem of CNF, okay? So sorry, just now I meant like over here, right? In a general CNF, in a general set, the size of the clause can be anything. It can range from like 2 things, 3 things, 4 things, or anything, okay? So this is for the general case, but for tree set is where each clause contains exactly 3 literals corresponding to different, and the thing here is, right, it's different variables. So you'll be guaranteed they start off with different variables, different literals. This is literals. Okay, so for example, I have a tree set instance here. So I have x1 or not x2 or x3, and x1 or x2 or x4. Okay, and this is a yes instance because I can assign these truth values: true, false, true, true, verify that it's fine. So true, true. So the nice thing about tree set, I think, like nifty, remember this is an OR, right? So as long as any single one of them evaluates to true, then everything evaluates to true. So I designed this specifically so that the x1 I can easily short circuit by saying x1 is true. I don't really care about everything else. Okay, so this is a yes instance. So you might be thinking like, at least I was trying to come up with a problem where it's a no instance, right? Then I remember like last time there's this very cool proof to show that all tree sets instances, if it's less than 8 clauses, so if I have less than like 8 clauses, right? If I have less than 8 clauses, all of it can be satisfied. It's all of them are yes instances, right? And the example of a no instance only exists if I have at least 8 clauses. Okay, you can talk to me if you're interested to find out why, but this is the no instance for tree set. It's very hard to find a no instance of tree set. Okay? And even if I can, it cannot fit on the slide, probably. It just confuses people. Okay, there's no point. So more examples, like again, like just to give you exposure to tree set, this is it. Then I color coded it to see, for you to see like which one matches to which one. So the same variable, same literal can appear multiple times across different clauses. Okay. Then the question of tree set is given a CNF formula where every clause has 3 distinct literals. Does it have a satisfying truth assignment? And to recall, tree set is NP-complete. In fact, it's kind of like the first problem, or is it circuit set? There's the first problem to show to be NP-complete. So in a sense, tree set is kind of like the grandfather of all NP-complete problems. Okay. So this is tree set. Any quick questions about tree set before I go on? It's important that you understand the definition, right? Because we are playing around with the definition of the problem. Okay. 941. Okay. Directed Hamiltonian cycle. Okay. So you might have heard about Hamiltonian cycle or path from CS1230 or any prerequisite discrete math class. But this is asking, is there a cycle that visits every node in V exactly once, every node in the graph exactly once? So here I have a graph, and it's actually a yes instance because you can find a Hamiltonian cycle, right? Verify it is a Hamiltonian cycle. And notice now, like it's very easy if I give you the Hamiltonian cycle and you just verify that it really is the Hamiltonian cycle, right? As compared to like you staring at it, where is the Hamiltonian cycle? It's much easier for you to verify. Okay, so this is the Hamiltonian cycle. And this is a no instance, right? This is a no instance because I flipped the direction of the arrow here. And then because of that, this is already a no instance. You cannot find a directed cycle such that it visits every node exactly once. Okay, so the problem, this is the two problems at hand. Now we'll be doing a reduction from tree set to directed Hamiltonian cycle. But before that, anyone have any questions? Please, if you're okay with this, give me a thumbs up. I haven't done this today, but I really need everyone to understand the definition of the problem before we go on. Okay. If you need me to repeat, let me know. Okay. Okay. Think seems like most of you are understanding the definition problem. So let's go on. Great. Okay, I see now everyone. So tree set to Hamiltonian cycle. Let's just recall what we are doing. We are doing a reduction, right? So overall, this is the whole picture. We are solving tree set, which takes in the Boolean formula. We perform a reduction. The reduction reduces it to a directed graph. And then directed graph, we assume that directed Hamiltonian cycle, we are magically given a solver for directed Hamiltonian cycle. It returns a yes or no, then we use that answer as the answer to tree set. This is the whole picture, right, of what we are doing. We are going to focus on this step over here, on the reduction. We're going to focus on the reduction. So to show it's a correct reduction, this is what I've posted a lot. Show that the Boolean formula Boolean formula is a yes instance if and only if the directed graph that you reduce to is also a yes instance, and the transformation takes polynomial time in the size of the Boolean formula. Okay. So again, what I encourage you to do, and if there's anything you can get out of this tutorial, even if you don't understand the reduction later on, is the thinking process that I think is more important. So think about the properties of these two problems. They look like they're very far apart. Okay, so let's dissect it slowly. Look at these two problems. What are their properties? So for tree set, and I think this is very useful to think about, is that remember, you need a way to encode the literal. You need a way to encode a literal. You need a way to encode that every literal is assigned either to true or false. Okay, so you need to encode a choice, like some form of choice that you cannot take back, because a literal cannot be both. It can only be exclusively one true or false. So encode the literal. Secondly, encode the clauses. Okay, so a clause property is such that if at least one of the literal inside it is true, then the entire clause is true. You need to think of a way for you to design inputs which follow this property. If one of them is true, then everything is true. Everything in the clause is true. Then encoding the entire CNF is usually just putting everything together. And steps 1 and steps 2 are the harder part. Okay, so think about these properties. Remind yourself what the properties are. Okay, directed Hamiltonian cycle is a very simple statement, but the properties is just such that all the nodes must be visited exactly once, and it forms a cycle. So these are the properties of directed Hamiltonian cycle. Okay, now let's go on. Oh, okay, wait. Before that, I'll use the term gadgets. This is very common in the literature, I think. It refers to some reusable construction for what we are reducing it to. So think of it as like representing literals or clauses or something like that. Or if you don't understand this slide, I think you will understand it in a bit. So just take note, I'll use the term gadget to just refer to a group of things so that I can easily construct more harder things. It's like an abstraction, okay? And again, I would like to emphasize that the arguments in the slides I present here is to just give an intuition. They are not fully formal. You need to fill in the blanks yourself later on if you write a proof like this. So they're not fully formal. But first of all, remember, we have tree set, right? We are trying to encode the literals. Every literal in tree set is assigned to true or false. How do I encode a choice in directed Hamiltonian cycle? Meaning, if I decide to go like that, if I decide to do a certain thing, I must only do that certain thing. I cannot go back and do something else. Intuitively, this is what we're trying to do. So let's design something I call the literal path gadget. And I use the property of directed Hamiltonian cycle, which is that every node is visited exactly once. I use this property to design something to help us encode this choice, this tree set true or false. Okay, so a path, the literal path gadget is a path in directed Hamiltonian cycle. This represents a single literal, right? So maybe this is representing x1, for example. It encodes the choice. And why does it encode the choice? Because I want to say that if I have such a path, I want it such that it only travels in this direction, right? If I go to the right, it means I'm setting the x1 to be true. But if I go to the left, then this is like setting it to false. Okay, is this clear? Anyone have any questions about this? Okay, so every time I ask like whether something is clear, maybe you can just give thumbs up so I can like be sure. First of all, this is the encoding. Okay, let me just wait for at least like 2 or 3 more thumbs up. Or people lost already. I see guys thumbs up now. So this is or maybe you need to see a construction. So let's see like how this is used. Remember, I'm trying to encode the choice in tree set. I want the literal to be either true or false. And I designed this path so that it becomes either true or false. Okay, so let's do it step by step. Let us have start and end node. So I'm performing the reduction to directed Hamiltonian cycle already. Okay, I'm designing the input. Given a tree set input, what do? I start off with the start and end node. Then I use the literal path gadget to encode a literal, right? This path 1 corresponds to x1. Then what do? I make connections. I make connections to traverse the path. Okay, need a way for the start point to traverse the path. Remember, we need to connect, right? So I say that, okay, either I start and then I go to the left or I go to the right, such that it can walk down the path. Okay, so this is path 1. We also do the second literal path gadget. This corresponds to x2. Okay, and then I connect the two ends of the path, and this looks like, wow, that's a lot of connections. This looks like a lot of connections, but why am I doing this? It's because, remember, I'm encoding true, 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 false, false, true, and false, false, right? If I have 2 literals, I need to encode true, 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 false, false, true, false, false. So this is represented in our graph as like going right, and then going here, and then going right. Okay? Let me use blue now. Or it is like going right, then going here, then going left. That's why you need these 4 arrows. Okay, so you need to be able to encode these choices. Okay, so I repeat for all 3 literals, and for simplicity, I only use 3 over here. But I hope the key part is like you need these 4 arrows, and then you just repeat the same process all over again for every literal. Okay, and then connect the final literal path to the end node, because remember, we want to visit all the nodes. Okay, finally, I want to cycle, so I go back. I point from T back to S. See, notice that all the arrows are like going in a downwards direction, so you need a way from T to go back up. Okay, so this is the first part of the reduction. Okay, and the idea is now that if we do this thing, we have 2 power n different Hamiltonian cycle. If we have n literals, this is the special case I said just now was the true, 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 false, false, true, false, false, which has like 4 Hamiltonian cycles just now. Either you go right, right, you go right, left, or you go left, right, or left, left. Okay, that's the 4 Hamiltonian cycles, but we generalize to 2 power n. So we are designing an input that has 2 power n choices. Okay, so this is the first step. For example, x1 is true, I go to the left here, right? I go to the left. I go from the left to right. x2 is true, I go from the left to right again. And then if x3 is false, then I go from right to left. And finally, I walk back up here. Okay, I walk back up there. Okay, let's take a deep breath. Anyone have any questions? Can you guys give me a thumbs up if you get it, or if you don't, please ask me to repeat. Okay, this is free, and like I guess since I'm just recording, I don't want to rush this reduction. So again, apologies, I'll be overrunning class a bit. Okay, so anyone needs me to repeat? Okay, I see less thumbs up this time, but I do hope that those who are not thumbs upping, maybe are just like still digesting. Okay, so this is the first part. This is the first part. So now, what we have done, right? What we have done is that we encoded a literal, whether something is true or false. What about a clause, right? A clause, oh, I didn't carefully like slide this. But okay, encoding a clause is that in our reduction so far, if we have three paths, right? How do we design a property so that if we traverse something in the correct direction, then we fulfill, okay, sorry, designing a property that is fulfilled only if at least one of them is traversed the correct direction. So again, like you can traverse the three path, right? P1, P2, or P3. But a true or false assignment is kind of like depending on the direction. So if one of the direction is a correct one, how do you assert that there's this property that will be fulfilled? Okay, it might be confusing, but let's just go through an example. So I'll use the visit every node property of directed Hamiltonian cycle. Remember, in directed Hamiltonian cycle, I need to visit every node. So I'll create an additional special node. I'll present a clause with an additional special node, and it can only be reached if one of the path is traversed in the correct direction. So here I have the special node over here. Okay, this is the gadget. This is the gadget. I have three paths. And then I connect path. I connect them like this. And this will be reachable. This C over here is only reachable if one of these three things is traversed in the right direction. This mimics a clause in tree set, right? If one of them is true, if one in Hamiltonian cycle, if one of them is traversed in the right direction, in the correct direction, then the entire clause is satisfied. So okay, so this is like the idea. So how do we do that in this graph? So recall what we have so far. We want to represent this clause, for example, x1 or not x2 or x3. How do I do it? I create a special clause node gadget. I create this gadget over here, and then connect it like over here. I go the correct direction if I go from left to right. Okay, so I go up like this, in a left to right manner. Then for x2, right? This is a negation. So if it's a negation, it's like going from the right to left. Okay, it's like going from the right to left. So therefore, the direction is first go up like that, then go down like that. Okay. Then x3 is, well, same as x1, right? So as you are going from the left, then you go up, then you go down. This is the reduction for the case of clauses. Okay, so I'm just showing for one clause, Then for the other clause, it's the same thing. It's the same thing here, just with a little caveat. You need this gap vertices over here. You need a gap node, which I'll explain why later. But the idea is this, right? So you really want, once a certain path is traversed in the correct direction, it reaches the clause, it reaches the node, reaches the clause node. Okay, so I'll explain in a bit why we need this. So again, let's give an example assignment, right? So I want to show that I have a directed Hamiltonian cycle given a particular assignment. Okay, if x1 is false, then I'm traversing like this. Notice right now, I cannot go up yet. I cannot go up. Like, because I'm traversing like this, I cannot go up here, right? And later on, we'll show why we cannot choose to go up, like if it's in the wrong direction. Okay. Then for x2, notice again, I'm assigning true to it. For x2, I'm assigning true. So I'm going from left to right. Okay. So again, the arrows don't support me going up and going down nicely. And for x3, this time is true, and I can go up nicely, right? So I'm going left to right. x3, I'm going left to right. Then I can go up and then go down, like very nicely. You notice I don't use this edge at all. I don't use that edge at all. Okay. So this is like a assignment. Okay. Then just completing directed Hamiltonian cycle. It's okay if you're confused. I think this is a pretty difficult reduction. I try my best to give like visual explanations. Again, take a deep breath. We are almost done with the reduction, or rather we are done actually. Now it's the proving it. So anybody have any questions? I'm gonna ask for thumbs up, but I won't be positive that everyone got it. But if you understand, really just give me thumbs up. I think that'll be reassuring if somebody actually understands. Oh no, no thumbs up this time. People are lost. Okay, if there's anything you would like me to repeat, please ask me now. Okay, I am gonna go through the remaining part just for the purpose of recording. Again, I'll be overrunning, so apologies. Okay. Okay, so I guess I'll complete the tutorial as it is so that there's a recording and you can visit it anytime. Okay. So the subtle detail is that we did not discuss the length of the path just now, right? I just say, okay, here's a path, but how many nodes should there be? Okay. Suppose we have K clauses. Suppose I have K clauses. How many? And you notice that the path is dependent on each clause, right? There are many nodes representing the clause. Okay. Suppose we have K clauses. And then each clause node gadget requires 2 nodes in the path. So I have 2K nodes. So each of this requires, sorry, each clause requires 2 nodes. So I have at least 2K nodes. And then including the start and end vertices, as well as the gap nodes I said was important. This gap over here, these gaps over here are important. In total, there are K plus 1 nodes. Okay, because right now I've for example, I have 2 clauses right now, but I need K plus 1 nodes later on. Okay. Then total, meaning I need at least 3K plus 1 nodes over here. Okay, the length of the path is 3K plus 1. Okay, so let us prove this correctness of reduction. Okay, so I want to show that the reduction is correct. Boolean formula to the directed graph, yes instance is if and only if, and the same routine actually, right? So proving the Boolean formula is a yes instance, implying directed graph is a yes instance, is pretty much by construction. Okay, so I have a yes instance means that it has a satisfying assignment. Let's say these 3 things are the satisfying assignment to the Boolean formula. Okay, so the constructed directed graph, well, it just say that, okay, for this path, go from left to right or go from right to left. Okay, and because this is by construction of our clause node, because we have a satisfying assignment, it means that there is one path where it's valid to be able to go up and go down like this. It's possible to traverse this clause node. Okay, there'll be at least one row where we go in the correct direction. Okay, there'll be at least one row where we go in the correct direction. Okay, so that's why this proves that if we have a Boolean formula, it implies a directed graph. So for example, as I mentioned earlier, this is a particular example. So if I have a satisfying assignment, show that I'm able to create a Hamiltonian cycle in this directed graph. Okay, so this is the first step. The second step is the other way around. Given a directed graph, if it's a yes instance, is the Boolean formula also a yes instance? Okay, the intuition here is that if you have Hamiltonian cycle, given the Hamiltonian cycle, you want to decide what the assignment should be. X1 is true, or X2 is true, or X3 is true, or false, whatever, based on the path that it traverses. Okay, based on this path that it traverses. Okay, so this is the intuition, what we want to do. The problem is it possible that we don't traverse the entire path? Is it possible that we get a Hamiltonian cycle where we go up a node and then we escape to another path? Okay, we jump over to another path. Is it possible that this happens? Well, it's not possible, and the intuition is that there are some unfazed nodes in the path, which means that there's not Hamiltonian cycle. If you escape to another node, to another path, then there are unfazed nodes in the remaining path. Okay, this is the argument, the intuition for the argument. But the formal way to argue about this is that even if you can't visit the rest, right, there might be some way for you to be able to visit this path, because maybe there's another clause node, and then you go up here, and then you go back down to P1. Maybe that's possible, but I argue that it's not possible. Why? Because even if you're able to escape, like first use C1 to escape to another path, and then go somewhere. You see this curve over here is I don't care where it goes, and then somehow I reach back to the first path, and I reach this node over here. I'll put a big star. I reach this node over here. Then you realize I get stuck. Why do I get stuck? Because if I go left, then I visit back a node that I've already visited. And I cannot go up. And I cannot go up anymore. So I'm stuck. There's no way I could have created a Hamiltonian cycle if it were like this, if I was stuck like this. Okay? So this is the first part of the proof. The second part, the second problem is that, okay, so that is you see like this node over here is not covered, right? So we cannot safely walk through this node. So what if we walk from the other direction? So we go over here, we go here, and we go up like that. So this is circumventing the problem that we got stuck. We got stuck over on the right here. Like just now we got stuck here, right? So let's walk through it in the other direction, and then go to the right to left, and then go up like that, and then go down. Okay, so let's say this happens. We also prove that this is impossible because you eventually get stuck as well over here because of the gap nodes. This is why the gap nodes are important. If you manage to escape to another path, if you encounter back to the left of where you escaped from, like over here, you also get stuck because it's a gap node. If it's a gap node, that means there's no way I can like connect to another clause. I cannot escape to another clause. So there's also stuck as well. So this is why the gap nodes are important. Okay, so in conclusion, okay, so I went through it a bit faster because I think most people are lost right now. If you are not, then that's great. Okay, but the intuition is, again, you need to be able to argue that it's impossible that the path is badly formed. Okay, the conclusion here is that when you're going through a clause node, you must go up and go down in the same path. You must start and exit the same path gadget. Okay, so again, every path must be fully traversed using the direction as the truth assignment. Okay, so I'll argue that it runs in poly time, and I think this is very fast, very simple. We have n literals, we have k clauses. There'll be n paths, right? So I have many paths. If I have three literals, I have three paths. Each of them have length 3k plus 1. So in total, it's onk. There'll be k clause node gadgets, right? So there'll be k of such nodes. And start and end nodes is O1. Okay. So and okay, I realize I didn't argue about the edges, but I think edges should not be a lot more either. Okay, so by right, I should argue the edges here as well, but you can see that this also runs total is onk time to create this graph. It's polynomial with respect to n and k. Okay, so this is the argument why the reduction runs in polynomial time. Okay, so I know it might be confusing, so you can revisit the recording again. You can ask me if you have any questions. So again, I must emphasize the arguments I present is just to provide an intuition. Okay, full proof will need more rigor, but if there was anything that you can get out of the tutorial, the reduction is probably not feasible for you to be tested like that in exam. But there's a thinking process. Remember, thinking what's the property of tree set I need to fulfill? How do I encode the choice? And in fact, when I was attempting your assignment, so there's a question reducing from tree set, I did this thinking process as well. And I think it helped me to come up with a reduction. Okay, so thinking that, oh, how do I encode this choice? And how do I encode that if something is true in the literal, then it's true for the entire clause. Okay, so thinking about that helped me come up with a reduction in your assignment. Okay, so what have we shown? Here's a quick question, right? So I know you didn't understand the reduction, but I argued with you that there is a reduction, right? Did we show that directed Hamiltonian cycle is NP-complete? Okay, I need you to understand this question. Okay, did we show this? You can PM me yes or no, or you can put it in the chat. Did we show that directed Hamiltonian cycle is NP-complete? We did a reduction from tree set to directed Hamiltonian cycle. Okay, I don't know if anyone's following right now, but okay, why? Okay, I received a PM no. Why? Okay, waiting for an answer. Wait for 5-10 more seconds. I mean, if I'm asking this, definitely is no, but the main reason is why. Okay, so I'll just reveal it in the interest of time. Is because if we show a reduction, right? If we show reduction from 3 set, we are only showing that it's NP hard. It's NP hard. For NP complete, we also need to show that the problem is NP. So we need to show that directed Hamiltonian cycle is in NP for you to show that it's NP complete. And I'm showing this because I feel that people will forget, we'll do a reduction, but will forget to show that it's in NP. So remember, show also that it's in NP. Okay, how you give the polynomial time certificate and then verify it. So, okay, these are exercises I prepared. You can take a look at it later. I think we are out of time anyway. So, okay, I'll skip this, but the essence of this is that, we don't have efficient solutions. So what can we do? Well, there are special things. We can do randomized algorithms. We can analyze special cases, and we can have approximation algorithms as well. So this is not in syllabus, the approximation algorithms, but these are things we can do to go around like the fact that we don't have efficient solutions. Okay, so as a summary, if you want to show a problem is NP complete, need to do two things. First, show that it's in NP. Afterwards, show that it is NP hard. The showing NP hard is really the harder part, where you take a problem A known to be NP complete and show that A has a polytime reduction to X. Okay. All right, so that concludes today's tutorial. Thanks a lot for coming, although it's a public holiday. But so if you're still very confused about the material, it's normal. I think it's very normal that it's confusing. So I tried to link like different things like MIT lecture on NP-Completeness, which very interestingly, it covers a reduction from 3 set to Super Mario Brothers. Okay, you might be thinking like, how is that possible? Okay, you can take a look at the video to see how. Okay, then there's this lecture slide, which I think is pretty nice. This chapter of this book is pretty nice, I think, as compared to the CLRS material, the textbook material. Then, yeah, some casual videos for you to watch. Okay, so thanks a lot for coming. I'll share the slides in the Zoom chat. Okay, so share the slide in the Zoom chat. And yeah, thank you very much for coming today. I will stay back for questions. Any question about the material? Oh, I received a question on archipelagos. I'll get to that in a bit. Yep, so go to okay, so the question in archipelago. So I have a question in archipelago. I think first of all, let me copy the question over so everyone get to see. Okay, so this is the question in archipelago. Can you explain more about integer program and the reduction from set cover to integer program? So I must admit the first part of the question, it's my first time seeing the reduction as well, but let's see if we can work through it together. Second part, do NP and co-NP cover all problems? So I'm not sure about the scope of this question, but definitely not, because what I see in this number line, right? I have NP hard problems. So actually, in fact, let me perhaps go to this video. Okay, wait, maybe I should do like MIT 6046J, then NP-Completeness. Okay, so let's just reference this lecture slide over here. Where's their number line? No. One second. So it's not because there are problems that are way harder. It doesn't cover all problems because there are problems that are way harder, basically. So let's go here. No, why don't they have the number line? I took the number line from them. Eh? Okay, never mind. So I'll just say that it's not covering all problems, because from this number line, there's actually like problems that are we call like something here, something we call EXP. This is problems that we know is impossible for it to be verified even in polynomial time. So it doesn't cover all problems, basically. NP only covers verifying in in polynomial time. But there are problems that are so hard, we don't even have an efficient solution for them. We definitely don't have an efficient solution for them. Okay, so these are like the problems EXP. There's problem we call undecidable problems. You might have heard of about the halting problem. So in halting problem, it's like the very end of the spectrum. It's like the very end of the spectrum, where even if you're given unlimited time, you are still unable to solve it. Okay, so it definitely doesn't solve all the problems. Okay, so that's the answer to the second question. So the first question is asking reduction from set cover to integer programming. Okay, let's go through it together. Okay, integer programming is given an m by n matrix A and integer vector B of length m. The integer program problem is whether there exists a vector x of length n such that. Okay, so let me visualize what's going on. So I have a matrix A, right? This is m by n and an integer vector B. So I have a result. Okay, so I want to ask whether it exists an x such that if you multiply these two together, if you multiply this, okay, this length should be longer. Okay, this is size n. This size n. Wait, sorry, this is size, sorry. This is correct. This is size m. If you multiply these two together, is it possible to find that it's less than that? So, okay, this is integer program. So, okay. Okay, less than for two vectors. That's a good question. So someone is asking for the meaning of less than equals to for two vectors. Huh. That's a good question. I didn't think about that. Let's Google for integer program. Integer. I suspect it's less than equals to for every single one of them. Integer linear program. Yeah, because I think, right, this is if you don't do it in matrix form, this is they separate the equations separately. So if I remember correctly, integer programming, you tend to separate the equation separately. You do equations separately, and all of them has to satisfy less than equals to. So I think for two vectors, it means that it's strictly less than for every single of its term. So if I have like x1, x2, x3, y1, y2, y3, the notion of less than is such that x1 is less than y1, sorry, and x2 less than y2, and x3 less than y3. I think this is the notion of less than for vector. I think that's a good question to raise up. Yep. Based on this. Yep. No problem. Okay, so this is the first step. Then, okay, so many problems natural reduced integer programming. Okay, Ken. Powerful heuristic to solve is to forget the constraint that x is this and allow x to be any. This is the linear programming problem for which there are efficient algorithms. We'll revisit this in week 12. Did Prof revisit this? I don't know. So, okay, so we argue that we reduce a set cover instance. Okay, before that, let's revise what a set cover is. Set cover is given integers k and n, collection of s subsets. So I have k, I have n, I have s of subsets of 1 to n. So like for example, say n is I don't know, 7. So s1 is like 3, 7, s2 is 3, 4, 6. So is it possible to find subsets? So find subsets such that the union is everything. Find subsets less than k subsets so that unioning them equals everything. Okay, so I've recalled the problem. So these are the two problems I had. We have integer programming, we have set cover, and the goal of this lecture is to find set cover to integer program. Okay, set cover to integer program. So direction is we start from set cover, reduce to integer program. Okay, then how do we do that? Let's see what prof does. Okay, so think about the properties. Let's think about the properties. X should somehow encode set cover. Okay, so I see. So X should somehow encode the set cover, meaning it seems that prof is saying this answer over here, this answer X over here should be the answer to the set cover. Okay, so we'll search for an X that is 0, 1 to M so that X1 equals to 1. If X, okay, I see. So I think what prof is saying here is that, so if S3, so, okay, please pardon me, I'm just going through this for the first time. So I'm trying to figure out what prof is saying as well. So if prof is saying is that because X is either 1 or 0, right? It's saying that I'll say if the answer X says that it's 1 in the first column, first entry, it means we take set as 1. So I think what I can see is that the n over here, the n here will be the number of sets. Okay, so I imagine this will be the number of sets, number of subsets. That's my guess so far. Okay, please we naturally want okay, what's this? We naturally want x1. We naturally want 1 to m, xi less than equals to k. What's this? Now I'm confused. I think this is saying, I see. Okay, so prof is saying we have m subsets. Okay, we have m subsets. Then it's saying a constraint we need in the integer program is so that I need less than equals to k. I need less than equals to k subsets in the answer. Okay, because the answer x, x1, x2, x3, if I try to sum them up, they must be less than equals to k. I need to be able to take less than equals to k subsets as part of the answer. Okay, is this okay so far? Each row of A gives a linear inequality to be satisfied by X for each I. So next part, each row of A gives a linear inequality to be satisfied by X. Okay. It says that negative of the sum is less than equals to -1. Why might this be? Each row of A gives a linear inequality to be satisfied by X for each I element of 1 to n. 1 to n, what's n again? N is the number of terms, right? So yeah, I think this is confusing because the numbers mix up. So I think n over here refers to the number of elements in set cover, I think. Each row of A gives linear inequality to be satisfied by X. Then it says that, okay, I sum up all the xj, and then I negate it and I get less than equals to -1. Okay, cool. Where does that come from? Maybe we'll see that in the proof. So let's see. Okay, let me understand this fully first. So okay, this is xj. For I in Sj, sum up everything in Sj. Sum up everything in Xj. Okay. Sure. Let me go on. Reduction clear in polynomial time. What? That's it? Okay. Reduction is clearly in polynomial time. Sure, this is polynomial time. Suppose there's a set cover of size less than equals to k. Then constraint satisfied. Suppose there's a set cover of size less than equals to k. Suppose there's a okay. So I understand the first. I understand the first row. Then what about the second row? For each j, each I element of n. If you understand anything from here, like since you're asking about the reduction, maybe you understand some parts, do let me know. I mean, like, I'm trying to understand the spot also. So suppose I have a set cover, right? So let's take the example of the set cover earlier. Here's the example of the set cover. Okay, so we have this example over here. Suppose we have this answer. Okay, I'm gonna delete this. Let's say I have S2 equals to 3456. S6 equals to 1267. Okay, so this is the set cover. If I have a set cover, you're not sure what A is. Okay. A is, wait, what's A? Oh, A is the matrix. A is the matrix. Second constraint ensures that subsets cover. Okay, so second constraints cover, yes, think that's reasonable. So for each j element of M, xj equals to 1 if sj is in cover and 0 otherwise, constraint satisfied. Okay. Ah, okay, so I sum up, ensure that I cover everything. So if for example, I manage to cover everything, I manage to cover 1, 2, 3, 4, 5, 6, 7, then the sum for each I element of Sj, okay, for each I element of Sj, yep, can. Constraint satisfied. Suppose the above most k xj's are 1, but those constraints, the other constraint make sure that each I element of n is contained. Yeah, so I think your question is more like what the matrix is, right? What the matrix A is. So we have the matrix, but you're not sure what the matrix should be. You're not sure what the matrix should be. But each contains the encoding for each subset. Yeah, I think so. So if I were to make a guess what the matrix might look like, so okay, let me think. Let's clean this up. Because I have 8, so this is each of the constraint, right? This is each of the constraint. So the matrix first row, okay, we need this to be less than equals, we need sum of okay, let me draw a more representative size. So this is, let's say m by n. This is n times this, then this is this. Okay, so the B, we need this to be K, right? This is the first constraint, then this is Xi. So the first row is all, I think this should be all ones representing this. Okay, so this is the matrix A. This is the first one. So the second one, I think for everything else is it's -1. Okay, so let's zoom into a specific row. This is for set S1. Okay, let's say I have let's say I have 7 things, right? Then this is like 1, 3, 4, and 7. This is S1. Let's say this is S1. I think what this constraint is saying is that this is -1, then this is 0, then this -1, this -1, 0, 0, and -1 because of the negative constraint here. So for each other row in A, you put a -1 if it's in the set cover. Sorry, if it's in the subset, if the value is in the subset. Otherwise, you put 0 because you're only adding I element of Sj. Okay, let me think if that's correct. Okay, so this is the X, right? So this is the matrix X. We want it to be less than -1 for each one of them. Wait, is that correct? Oh, wait. Sorry. I think I made some mistake. You are right. Now I'm confused by the matrix.
Yeah, actually, I don't know what the matrix is supposed to be. Is it the same for both constraints?
I'm not too sure whether it's the same or not. Tell you what, I'll look into this in more detail. Then I'll let you know if I figure out something.
Yep.
So sorry.
Yeah.
Yep.
Okay, thank you. Bye.
Yeah, thanks for coming.
Thank you.
Okay, so I guess I'll review that matrix example, then I'll get back to Okay, so thanks for coming today, and thanks for watching the video, since most of you are probably watching the video. So yeah, let's end the recording.